tutorial, and then you'll have other tutorials. Okay, tonight we're going to talk about induction, we're going to talk about summations and logs, and we're also going to talk about arithmetic proofs. So let me write that here. So induction is a method of proof, and we're going to be using induction to prove lots of statements are true for large sets. So we've been talking about finite proofs where we have variables, you know, like 4 variables we're combining and doing logic proofs, and we're going to find one thing is true. But if we want to prove something is true for a large set of things, then we need to use a method that will show that something is true for all, say for all numbers, without us having to sit there and demonstrate everything. So for example, let's see, let me do prove n squared minus n is always even. So there's a problem that we're going to do, and I'm going to show you 2 different ways to do it. One way we're going to do is called by arithmetic proof, and one way is by induction. So anytime you have something that's fairly simple like this, you should be able to do it with an arithmetic proof, but you can also prove anything that you want to prove for all numbers, such as all integers maybe. You can also do it by induction. So first let's do it sort of arithmetically. So what does being even mean? Divisible by 2. So I could write it as a product of 2 and some other integer, right? So that means that I would be proving that n squared minus n is equal to 2k, where k is in the integers. So one way I could do that is by considering whether n was even or not to begin with. Does that sound reasonable? I could think if it was even, then obviously n squared minus n would be even, right? Because that's a sum of 2 even integers, or a subtraction of 2 even integers also. So let's consider the case 1. Case 1, n is even. And we know there's only 2 cases. It's either even or odd. So if n is even, let's say that's equal to 2j. Because that's the definition of even, is that it's a product of 2 and another integer. So if n is equal to 2j, then n squared minus n is equal to 4j squared minus 2j. And so if I want to prove that this is even, I have to be able to factor out a 2. Because we know that integers are closed under addition and subtraction. So if I add 2 integers, I end up with an integer. If I subtract 2 integers, I end up with another integer. So these things here, it's still an integer. This combination of numbers and letters is still an integer. If I can factor out a 2, that's equal to 2 times 2j squared minus j. This number here is an integer, right? Because j is an integer and so is 2, and these combinations of multiplying, adding, and subtracting them are integers. What's the only operation we normally do that isn't closed for the integers?
Division.
Division, right? If I divide 2 integers, I don't necessarily end up with an integer. So now that I've written this as 2 times an integer, therefore n squared minus n is even for this case. So all I have left is to prove that when n is odd, I still have n squared minus n is even. Okay, so I have one more case.
J is an integer. I mean, couldn't it be like 1/2 or?
That's something I assumed here. J is an integer. If n is even, it's the product of 2 and some other integer.
Okay.
So that was an assumption. When I wrote that n equals 2j, I was assuming that j was an integer, because otherwise n wouldn't be even. So if I write an even number as 2j, how do I write an odd number? Odd numbers are definitely not divisible by 2, right? So I could put 2j plus 1, and that would be always an odd number, and every odd number I can write that way, right? If I pick the right j, I should be able to write any odd number in the form 2j plus 1. So let's do case 2, where n is an odd number. So that'll be case 2. And the final case also. So n is odd. That implies that n equals 2 times j plus 1, where j is a member of the integers. In that case, then we want to see what happens to n squared minus n. So we're going to plug in 2j plus 1 for n and square it, and then subtract 2j plus 1. And we want to be able to factor out a 2 in the end. That's the whole goal. So this is going to be equal to 4j squared plus 4j plus 1 minus 2j minus 1. So that looks pretty good because our plus 1 and minus 1 are going to cancel, and then everything left is divisible by 2. But just to make everyone happy, we'll combine those j terms to get 4j squared plus 2j, because I have 4j minus 2j, and that's equal to 2 times the quantity 2j squared plus j. And we're happy because this is an integer, and we factored out a 2, so therefore n squared minus n is even. And since for both cases we have that n squared minus n is even, then we know that n squared minus n is always even, because all integers are either even or odd. Trick question, is 0 even or odd?
Neither.
Well, it can be divided by 2.
You have to, that's a tricky question, right?
Right.
Would I write 0 equal to 2j, or would I write 0 equal to 2j plus 1?
0 equal to 2j.
I would pick this one. Because there's no j I could plug in there and get 0. I can plug j equals 0 in there and get that 0 is equal to it. I can divide a 2 and have a remainder of 0, and that's really the definition of even, is if I divide by 2, I have no remainder. So 0 is an even number. It's not positive or negative, but it is even. Okay, so that was an arithmetic proof. In arithmetic proofs, we break the integers into groups of numbers, and then we prove the property that we want for every single group, and then once we've proved it for every group, we're done for all of the integers. So we can do that. Here we were talking about divisibility by 2, so if I wanted to show that some combination of letters together was divisible by 3, I would break n down into 3 cases. I would talk about n equals 3k, n equals 3k plus 1, and n equals 3k plus 2. So I'm not going to do an example like that today, but what I am going to do is a proof by contradiction, an arithmetic proof by contradiction. So that was a direct proof, a direct arithmetic proof. Let's do an